Well, this is a lecture on unbalance detection. In fact, this is the first of the series of this module, wherein after having understood the rudiments of signal processing and of course, the elements of machinery maintenance and condition monitoring, we are now specifically coming to how do we detect different kinds of faults in rotating machines. And to begin with, we are going to start with unbalance, the most common form of mechanical defect in any rotating machinery. Well, now before we begin into this lecture, let me tell you what do we mean by unbalance. Okay. As you all know, in this machines of ours, we are always going to have shafts which will be rotating, and these shafts are supported on bearings, and these shafts will be rotating at very high speeds, low speeds, whatever. Now, if for some reason there is an unequal distribution of the mass which is rotating around this center line, geometrical center line of the body, and there is a small mass m. Okay. This mass, because it is not uniformly distributed, is going to give a force m omega square r, okay. And this force is going to be radial in nature, going to be a function of the speed, function of the distance of the unbalanced location from the center of axis. And because of this extra force which is coming onto the system, the rotor or the shaft in this case, there will be extra reaction forces, or in effect the bearings are subjected to forces much more or beyond what they were initially designed and selected for. When a designer selects a bearing, they know the radial loads coming to that bearing, and then they design and select and design the bearings. But on top of it, if I have this extra force, they are going to add to it. And another problem you will see is this force is not a constant force as a function of time. Since it is rotating, this force is also fluctuating. So, this compounds the problem, fluctuating force. So, if you will recall your fatigue design of shafts, because of such fluctuating forces, the material of the shaft is going to fail quickly in comparison to the case of a static force. Okay. So, presence of an unbalanced force leads to such excessive fatigue force, and then that leads to a failure of the system. Okay. So, now let us look at it from a different perspective. Let us look at a disk which is rotating. This has an initial mass, has a mass m rotating. Okay. So, this has a radius r. At some location E, I have a small mass m at a location of E. Okay. So, the amount of unbalance can be unbalanced force can be written as given by this expression. Okay. So, we can define the for a particular let me take this back here. Okay. I will define the unbalanced mass. I'll come to this expression later on, okay, wherein we can define the amount of unbalance. I'll first define it and then come back to this slide. Now, this disk could be thin, which is rotating about the shaft, this is a thin disk with an unbalanced mass here. So, in this case, if I support this disk on knife edges like this, okay, and this is going to always come down because of gravity to this location, and this is the case of a static unbalance where the forces are only in one plane. Unbalanced force is in one plane. Now, imagine instead of this disk, I have a long rotor like the rolls of a paper mill. If I have an unbalanced mass at this location and if I have an unbalanced mass at this location, so this is giving me an unbalanced force in this direction and this is giving me an unbalanced force in this direction. So, from a force point of view, this is balanced, okay. But you see this, because they are in different planes, they give rise to a couple. Okay. And this is what is termed as dynamic unbalance. In some books or some literature, they say this is a coupled type of unbalance, and then they have a dynamic unbalance where these forces are actually inclined to some axis. Okay. Okay. But in our class, we are going to treat one as the static unbalance and other is as the dynamic unbalance. So, in the case of static unbalance, it is very easy to balance it by estimating what is the amount of unbalance. I can put another mass opposing to it and then balance it. In the case of dynamic unbalance, just balancing these does not happen. We have to put some more weights in another planes, so that the couples are also reduced or couples are balanced. We will come to dynamic unbalance later on. Okay. Now, of course, one of the fundamental assumptions we are doing in this balancing is or unbalance is these are rigid rotors, but you know from our class of the rotor dynamics that the rotors have many degrees of freedom and then they need to be treated as flexible rotors. But as long as the operational speed of the rotor is less than the critical speed, of course, to begin with the first critical speed, I can consider it to be a rigid rotor, and balancing at one location or putting a weight at one location balances the shaft. But when I talk about steam turbines or gas turbines, where it is a long shaft having sets of compressors vanes and turbine vanes. These are long shafts, and as you know there will be many critical speeds. Okay. So, balancing may not be possible in one plane, because if I think of the mode shapes of the shaft at many speeds, this could be a mode shape, this could be the second mode shape, this could be the first mode shape, and so on. Okay. Sometimes because of mode locations, this may have no motion, but then if I balance here, try to reduce it, okay, but then I am not doing anything here. Okay. So, in the case of flexible balancing, we have to balance in different planes. Okay. And of course, we always should not run at the critical speed, away from the critical speed, just so that we do not have the condition of resonances. But in this class, our attention is focused to these rigid rotors, and we are looking at operational speeds less than the first critical speed. Okay. So, balancing can be a very complex phenomenon. When you are talking about long rotors, large rotors, when there are sets of discs, could be compressors, could be turbines, could be some sort of blower fan sets. When if it is a long rotor, it is a flexible rotor, there will be many critical speeds, and it is a difficult task to balance those multi-plane balancing. Okay. Though people do that, there are software which can do that, but in this course we will focus our attention to very simple, maybe a Jeffcott rotor with a shaft which is rotating below the critical speed. It has a disc which has an unbalanced mass. How do we balance it, and what are the effects of it, and how do we detect such unbalance? And that is the first part which you need to look into it. Well, before I go into how we detect the unbalance, what are the possible sources of unbalance? One, of course, if the component, for example, many components in rotating systems are casted. For example, in an automobile, flywheel is a very important component in a IC engine, could be particularly in the single cylinder or two stroke engines, couple of cylinders. Of course, and if you have more number of cylinders, the cycles are balanced, and then the flywheel will be of a lesser size. But I am talking about a single and a 4-cylinder, 3-cylinder engines, wherein the flywheel is mounted after the clutch, okay, after the crankshaft, so that we reduce the cyclic engine variations. And imagine such a flywheel has an amount of unbalanced mass. So, this is going to give an unbalanced force onto the shaft, and this is not desirable, and usually flywheels are casted. Okay. There are many engineering applications, I will tell you. For example, you would have seen the alloy wheels in the automobiles. Wheels, or particularly they are the rims. Okay. Say okay, on which we have this is the tire, this is the rim, and this could be an alloy wheel rim. Okay. And which is actually casted. You can understand, if this casting has a defect or there is some sort of an unbalanced mass, every rotation of the wheel you are going to get a force like this. Okay. And imagine the scenario, it can be complicated. If you have a vehicle which 4-wheel drive or 4 wheels, and everyone is giving a force, they may not be in phase. When one is giving the force in this direction, other is giving it in this direction, other is giving it in this direction, other is giving it in this direction. So, imagine you ever have an erratic motion of a vehicle, okay, and these are undesirable, okay, bumpy rides, forces coming from the wheels because of unbalance. So, I am sure all of you must have realized it or witnessed when we buy a tire and we mount it on the rims or rims. Okay. They have, and if you go to any automobile garage, they have wheel balancers. Okay, they advertise that because and then if you notice, particularly not in the alloy wheels from the front, you cannot see, but if you go to the casted steel wheels, you will see a small amount of weight given here, depending on, because after the balance, they would have attached a balancing weight to it. Okay. And those of you who are riding bicycles must have experienced it if you have a bad tire. Okay. We always do that when we are students. Okay. If the tire was weak, we did not have enough money to change the tire, we would go to the cycle guy, then he would put a layer of cut tire in between, okay, and then you would have a patchwork. And then if you rode that kind of a cycle, you would get a periodic hits on your seat, okay, bumps. Okay, this is because of unbalance. Okay. Now, imagine if this kind of things rotate at very high speeds omega. So, forces will be very high, and these forces are finally taken up at the supports. So, bearings will be subjected to fatigue damage, and then they will fail much quickly. Okay. First is unpleasant ride quality in vehicles, and then bearings will be getting subjected to fatigue load. This will be not good for the machine or the cycle or automobile in this case. This is true for the case of fans and blowers, particularly in industries. I'll come to that just in a while, a little bit. So, one possible source of unbalance is whenever we have casted components, there could be casting defects, blowholes, which leads to uneven distribution of the mass, and thus we have the case of unbalance. One is another one, the next one is the case of certain installation issues. Imagine we have a large system, okay, and which has to be put in place perfectly between the bearings, okay, and they have to be in the geometric center line of the system. Okay. Now, imagine if this was not in the center line, okay, and there was a slight offset. Okay. So, this is going to give rise to unbalance. So, when the geometric center does not match with the line which connects the center of mass, then there will be a problem, and then things will wobble. So, wobbling will lead to the case of unbalance as well. Okay. So, while installation, people have to take care of these issues also. Another case which happens is the case of maintenance. Particularly in the plants wherein we have a lot of blowers, maybe a FD fan, forced draft fan, FD fan. FD fan, basically what happens when you have this is a chimney, okay, and then we put an FD fan here. and these are the gases, okay, which are after burning the coal actually. Okay. There is a lot of fly ash in these gases. Okay. What happens? So, because to give an extra draft to the fan, we put a fan, and this fan basically pushes out the gases out of the chimney, because the chimney is at a certain height, because we do not want to release the gases all around us. We send it high up and then send it so that they disperse and can fly off to large places. Okay. The problem is with fly ash. Fly ash on top of it, if it is wet and moist, they will become like a sludge, and then they will, these fans have blades. I am just, so with time what happens, these fly ashes get deposited, they stick to the fan blades, okay. And then once they stick, they may not stick uniformly, in some location they may get stuck, okay. And then this gives rise to a fan which is unbalanced, and then I have seen cases wherein these fans are failed, the blade shear off and the bearings get damaged because of this excessive fatigue force, which went unnoticed because things got deposited in the blades. This happens in a lot of chemical plants and food processing plants also. When you are talking about say dry milk powder, okay, you have seen how the dry milk powder becomes sticky once it gets in contact with moisture or water. Imagine when you have in the milk processing plant, they have a lot of agitators and mixtures. Okay. Agitators and mixtures are nothing, but again some high speed churning devices in a tank. Churning devices. Again the same thing, if I feed in certain material which is susceptible to moisture and then it becomes sticky, they will stick to the blades, and then because this is rotating, then unbalance, and finally you will say some fine day this thing has failed, okay, because of excessive fatigue loading. Again these things happen. So, periodically in many of these plants, be it the FD fan in a power plant, be it an agitator in a food processing plant, periodically in regular maintenance they scrape off, and there are alarm levels also. If suddenly they see that the weight increases, etc., they know that something is getting deposited. You are talking about iron ore sintering plant, okay. A lot of things happen, okay. A lot of places where things can get stuck, they will create an unbalance and then things will break off, okay. So, the sources of unbalance are manufacturing defect, installation issues, maintenance issues, and so on. And then the question is, what is the tolerable limit of unbalance? Okay. See, everything can be balanced, okay. But how less should this force be reduced to and how much should be acceptable? This is a function given by this curve here. One, it says the speed of the machine, and other is the acceptable residual unbalance per unit of rotor weight, that is given is gram per millimeter per kg, where the denominator is the so acceptable unbalanced mass because if I unbalance force is m e omega square, if I remove the speed unit out, F by omega square is equal to m e. So, either I can say as gram per millimeter, okay, and then if it is a particular speed, I know what is residual, and the mass, this is the mass of the rotor in kg. Okay. So, for large levels, G 830 means a very high mass rotor, and if you will see, this is G 0.04, and with speed, okay, the amount of unbalance which you can tolerate obviously will reduce, because with speed anyway we have a very high force omega square. So, obviously at the same grade will have higher levels of acceptable unbalance at lower speeds, that is obvious, intuitive. Okay. And this is the case of a precision balancing. Imagine in watches, etc. If there was this was not precision balanced, okay, then we will have a lot of problems. But when I am talking about maybe a steam engine or a big drum, okay, big cement mill drum which is rotating at very low speeds, the numerator can be very high. Okay. So, depending on the grades of unbalance, this chart is given as per the ISO 1940 standard. They have classified the grades of unbalance as to how much of acceptable quantity is unbalanced, how much is not balanced, when we should go for unbalancing and so on. So, this is a grade, it is a reference, because we never know. I have got a residual unbalance of 1 gram rather than 0.1 gram. Is it okay? Is 1 gram okay? Is 0.1 gram okay? Is 0.01 okay? Or 1 kg okay? We do not know. Then we have to follow this standard, and accordingly we have to specify that. Another very important thing we have to keep in mind is, of course, we will talk about this in the next class. Balancing or unbalance is defined or specified at a particular operating speed. Okay. If I have balanced a component at a particular RPM n by n RPM, okay, obviously the amount of unbalance will get magnified if I make if I operate it at n star, which is much higher than n, because of the omega square term. The residual unbalance which was there will get magnified if I increase the speed. So, it is always safe to balance a system at its operational speed. Okay. Otherwise, if I operate, suppose I balance it at 2400 RPM and then try to operate it at 4800 RPM, I am magnifying the amount of residual unbalance which is there. So, usually best rule of thumb is, suppose it is operating at 600 RPM, you also balance it at 600 RPM. Okay. But usually there is a problem that we do not have high speed balancing machines. So, usually people try to do it at a lesser rotational RPM and then try to operate it at a higher RPM. But we have to be careful that we do not run it at too much of a higher speed than it was intended to be balanced for. Now, this is a typical balance quality grades. This is from the same standard of ISO 1940. Now, you say this balance quality grade, it says Z 0.4. This is basically for spindles, disc, armatures, precision grinders and gyroscopes. I will just come to G 100. This is the crankshaft drives of fast diesel engines with 6 or more cylinders, complete engines for cars and trucks, G 100 grade. Okay. When you have say G 1600, crankshaft drives of rigidly mounted large 2 cycle engines and marine engines, etc. So, for small gas turbines, steam turbines, rigid generator sets, it is G 2.5. So, balance quality grades which we have to balance is actually specified by such standards. Okay. Now, question is, with this brief understanding of unbalance, what are the effects it can have on systems, because many machinery components actually start failing because of unbalance. Because see what happens, unbalance gives rise to excessive forces at the supports. So, supports, the bearings will then get damaged. So, we may be alarmed because of a bearing failure. The initial problem could be something else, could not be bearing failure. To say that again, unbalance, if it goes undetected, unbalance is going to give rise to forces at the bearings. The bearings are subjected to high forces, the bearings are going to fail, and then we will be, maybe if the bearings are making noise, etc., bearings fail, shafts are going to fail. So, eventually we will be drawn to a failed bearing or a failed shaft, but the initial culprit could have been unbalance, which was undetected. Just for that examples I told you, something is getting deposited on the vanes and blades which went unnoticed. Okay. But there are many ways to find out unbalance, and vibration again is a helpful tool to help us detect vibration. And I will give you two specific examples how vibrations helps us detecting unbalance in a couple of cases. In one case, we have a rotor, maybe on this rotor we have a disc which has an unbalance, and then we have this rotor supported on bearings, and what I do here is I put a accelerometer say axle 1, axle 2, and there is an unbalance. So, I am getting a m omega square E unbalance force. Now, of course, if you look in from the side, the rotor will look something like this. So, this is my vertical direction, this is my horizontal direction, and of course, this is my axial direction. Okay. In this example, I am measuring the vibrations at two locations. This is bearing 1, bearing 2, because I can obviously only put the accelerometers at fixed rigid locations, and these are necessarily bearing 1 and bearing 2. So, imagine what is going to happen because of this unbalance. This shaft is going to bow. Okay. So, because of this bowing, because of the unbalanced force, I am going to have very high vibrations. Okay. They will be this vertical or horizontal. This accelerations will be much higher than the axial, and they will be at the 1x frequency. By 1x frequency, I mean it is at the rotational speed, fundamental rotational speed. Fundamental rotational speed. Okay. And this is strongly harmonic, because you can understand if the rotating unbalance with every time it is going to change. Okay, it is going to be a sinusoidal. Okay. So, because the sinusoidal motion, I am going to have it's a harmonic, and obviously with speed, because of the omega square term, the vibration amplitude is going to increase like a parabola, okay, with time. Sorry, this is with omega, okay, because of the square term. And another very important thing which you have to notice in detecting of such unbalance is, this is in phase between the support of the bearings. That means, by in phase I mean, whenever the acceleration at location 1 is a maximum, the vibration at location 2 is also a maximum. So, that means the phase relationship between them is 0 degrees or close to 0 degrees. That means they are in phase. If I was to plot in an oscilloscope, if I draw two lines here, this for V1, V2 time. Okay, this is for bearing 1 and this is for bearing 2. By in phase, I mean whenever this guy is maximum, this guy is a maximum. Whenever this guy is a minimum, this is a minimum. So, they are all in phase. Or the phase difference between them is 0. Okay. But this is very ideally speaking, it's nice to tell it in notes, but once you go to the fields to measure, because no system is perfect. When I drew a sinusoidal, if I show you an unbalanced time history of a signal, this is nowhere close to this, because in a machine everything is mixed up. This sensor which we put on the bearing, okay, this measures a lot of things. This measures the bearing vibrations on top of the unbalances. Okay, this measures suppose the shaft had some other problem, like a things were loose, shaft had a crack, shafts were misaligned. So, all these vibration signals are going to come into this accelerometer here. So, these are the diagnostic techniques or routines which we have to follow to ensure that it is unbalanced and not looseness or misalignment or crack shaft. So, these are the processes by which we can know or we can be sure that yes, there is an unbalance, because I am having a high radial force or a high radial vibration compared to the vibration in the axial direction, and then of course, the vibrations between the two bearings are in phase or they are at 0 degree. You may not quite get 0 degree, you may get 10 degree, 20 degree, but well, this is not 0 because of other reasons, but then we are going to get a sure test that this is the case of unbalance. Okay. And this configuration is true when the rotor is in between bearings, and as I told you right in the beginning, that we are talking about the balancing of rigid rotors in a bearing where the rotational speed is less than the critical speed. But there could be another configuration, there could be, or before I go here, I just want to show this. This is what we have measured here. Now, you see, we measured signal 3 is one accelerometer, signal 2 is one accelerometer, which you have mounted on. Maybe if I go back and draw it here again. Okay, this is my channel 2, channel 3, wherein we have a disc, I will show you a picture of this setup in the next class. Okay. And if I look here, and this is the in phase vibrations, and the top plot is the cross spectrum. Okay. Cross spectrum establishes the delay between each other. In this case, we have the phase and the magnitude. Most important is the phase here, and this was rotating at 24.06 hertz and close to about 1440 rpm. This corresponds to about 24 hertz. Okay. And you can see this is about 24.063, because this is what the finally the shaft was rotating at 1440 rpm. Okay. And then in the sorry. If you will see this dotted line here, if you can see it, here the cursor has been put at 24.063 hertz, and the y in phase is about 13.149 degrees. Okay. And if of course, the cross spectrum you cannot see here, but actually it should have been the magnitude, and you will see a very strong component in the cross spectrum. Of course, you would have seen the auto spectrum as well, and this indicates that there is a high level of vibration. I have not shown you the actual vibrations, that was too less in this case, and this was actually simulated in an experimental rig, wherein we introduced a mass of unbalance and rotated it and measured the phase between 2 and 3. I did not report here the actual directions because it was too less, but all you have to, I wanted to show you regarding the in phase vibrations, and they are in phase. Okay. Another case is when we have a case of an overhang rotors. In case of an overhang rotors, the configuration is like this. I have a shaft onto which I put a disc, and they are supported on 2 bearings, and this is the overhang part. Okay, and they are rotating. Okay. Now, in the previous example, when the shaft was supported in between 2 bearings, I had told you that there will be strong radial vibrations. In overhang vibration unbalances, there may be also strong axial vibrations. So, this direction as well as this direction. Okay. And though the axial vibration may be unsteady, and axial phase between these two may be little unstable, they may not be stable. Okay. And this is again a case of an example wherein on the overhang rotor unbalance can be detected. But the problem with unbalance detection is many. So, what are the problems? Associated with unbalance detection. One problem is, whenever we have an unbalance or we have a machine rotating at a particular speed, I will get a harmonic vibrations because it is periodic vibrations. If I look at it in the frequency spectrum, I will always get a 1x component, and this is because of the rotational speed. But think of it, any machine, it has to rotate at its rotational speed, and so in any vibration measurements I am bound to get this rotational speed in the spectrum. So, this may be misleading. I have seen many times people, when they see a rotational speed, they say, well, no, it is unbalanced. That is not true, because this rotational speed is fundamentally, because of the physics of the problem, it is there. Of course, this can be less, this can be more, but think of it this way: if this was misaligned, this was bearing, I am still going to have a rotational speed coming up. So, just seeing in the spectrum a frequency at 1x, you should not be biased to detect unbalance. So, 1x does not mean unbalance. This is very, very important, because the reasons of 1x are many. It is a fundamental rotational speed. It is there could be looseness, there could be misalignment, there could be cracks, there could be bearing defects. So, how do you say for sure that this is an unbalance? And that is where you look into the phase relationship between few transducers. That is when you look into the relative amplitude between the radial and the axial. Okay. So, because many times another problem is only radial data is available. Okay. Number 3, which is common to any machine, is rotational speed not known. For a system, simple rotor system, wherein we can measure the rotational speed of the shaft, is not a problem. But think of a multi-stage gearbox. Think of a multi-stage gearbox, wherein I have an input shaft, and of course, there are a lot of intermediate shafts, and then I have bearings at every location. These are all the different. So, the speeds of this intermediate shaft sometimes are not known, because I do not know the gear ratios. And there could be a problem of unbalance here, because of one tooth broke, it fell, it created an unbalance, but I can put an accelerometer here and measure. So, if I do not know the right rotational speed, I am not able to pinpoint what is which shaft is having an unbalance. So, these are the problems associated with unbalance. Another thing is very, very careful is when we have to compare the radial, that is the vertical and horizontal, with axial. We have to be sure that they have been calibrated, the accelerometers are calibrated, and when I say, I mean 10 meters per second square in a particular direction, I also mean that this has been calibrated for that level. Otherwise, when I am getting a value of 10 meters per second square here, and this was not calibrated, I am getting a value of 8 meters per second square. There is no way I should be able to compare. I should be comparing these two. So, people mistake or miss these instances when they do the unbalance detection. Okay. We have to be careful that these kind of problems are taken care of. So, to summarize in this class, we looked into the causes of unbalance, or in fact, first we defined what is static unbalance and what is dynamic unbalance, how we define the grades of balancing, and then most important is to know what is the source of unbalance in a system, and then how do we detect unbalance. So, the source detection is very, very important. Now, once we have detected unbalance as opposed to other mechanical system faults like looseness, misalignment, cracks, through signal processing or through the signal processing of the measured vibration, we can pinpoint and be sure that an unbalance has occurred in the system. And in the next class, we will see that how this balancing can be reduced, and then how we can balance a system which is rotating. Okay. Thank you.